Hello everyone, this is Dr. Webb and welcome to this Calculus 1 video. In this video we're going to be talking about how to take derivatives of functional inverses. So suppose you know about a function and you know what its derivative is, and then you want to figure out how to take the derivative of its inverse of f to the minus 1. So this is all going to revolve around the chain rule, and so here we have our chain rule, which we've been using quite a lot lately. And so remember, the chain rule is if we have one function plugged into another and then we want to take the derivative, then that's equal to the derivative of the outside with the inside plugged in, and then times the derivative of the inside. And so specifically we're going to be talking about when the function on the inside function, the g of x here, is actually the inverse of our outside function, f. So if we plug our inverse in, then what's the chain rule going to say this is going to be? Well, f has stayed the same, so it's still going to be derivative of f on the outside, but now we're going to have the inverse plugged in, and then we're going to have this derivative of the inverse function on the outside. And so this is what we're trying to figure out. This is what we want. And so there it is, written all nicely. And so that's one way of thinking about it. On the other hand, we have an inverse plugged in. We have a function with its inverse plugged into it. And by definition of the functional inverse, these two cancel themselves off. Right? And so these cancel themselves off, and so really on the inside we're just taking the derivative of x. Right? So on the left-hand side we're just taking the derivative of x. On the right-hand side we're using the chain rule to figure out what this is. And the nice thing about the derivative of x is that it's just 1. And so we have 1 is equal to the derivative of the function with its inverse plugged in times the derivative of the inverse. And again, this is what we want. And so at this point we can just solve for it by dividing both sides by the derivative of f with the inverse plugged in. Same thing over here to cancel it off. And we're left with the derivative of the inverse is equal to 1 divided by the derivative of our original function with the inverse plugged in. And so this is our formula for derivatives of inverses. Okay, so let's talk a little bit about what's going on geometrically here. Right? So here, our green function is our original f of x. This is the function that we know how to take derivatives of. And then the blue function is its inverse. And so this is what we're trying to figure out, what the derivative is. And so we're starting off with a point on the inverse function. And so the x value is at a, and then the y value is the inverse value of that. Well, so since these two are mirror images over the line y equals x, that means there's sort of an associated point where you just flip the x and y coordinates on our original function f of x. So that the x value there is f inverse of a, and the y value is a. Right? This is what it means for these functions to be inverses of each other. If you swap the x and y coordinates of one, you get a point on the other function. Okay, so now let's draw out the tangent line on our original function f of x. Right? And so we know this tangent line is going right through this point. And so we know what its derivative is. And that derivative is going to be the slope of this tangent line. And so the slope here, the change in y divided by the change in x, well, this is going to be the value of the derivative at this x value. And so that is f inverse of a stuck in there, right? And so if you think about this is a line, and so for any change in y and any change of x, you're going to have the same value. And so in particular, I can set delta x to be 1, and that means that delta y is f prime of f inverse of, this should be at a. F prime of f inverse at a over 1. Okay, and so same as these functions are mirror images over the line y equals x, the tangent line is going to be a mirror image too. And so we can just flip this tangent line over. Okay, so here is the tangent line for the inverse there now, and these are mirror images over each other. So this triangle we made over here, this is actually going to reflect over and make a nice triangle over here with a similar slope. And whereas if we think about delta y was being vertical, well, when it flips over, it's going to be now on the horizontal side. And so this delta y was equal to the derivative with f inverse plugged in. And so that's what we're going to have on this side. Derivative with f inverse of a plugged in. And then the base, delta x, remember about delta x, we can think about setting that to be equal to 1. So we have 1 over there. And now on this side, if we're thinking about the slope over here, rise over run, now 1 is talking about the change in y values. And the derivative of f with f inverse of a plugged in is now talking about the change in y values. And so the slope of this tangent line is actually equal to 1 over the derivative of f with f inverse of a plugged in. And so that's geometrically what's happening here. And so this reflection over the line y equals x, this is actually taking the reciprocal of the slope. And so the slope of our original tangent line, when we flicked it over, we're going to get a reciprocal slope on the other side. And so that's what's giving us this formula. Okay, so now that we have this formula, let's apply it to find the derivatives of some functions like square root of x. Right, so if we let our f of x be x squared, that's going to make our inverse function square root of x. And so the derivative of x squared, we've seen that quite a bit before, that's 2x. And so now we have everything we need to plug it into our formula. And so we get that the derivative of square root of x is going to be equal to 1 over our derivative, which is 2x, with f inverse plugged in. And plugging that all in, we get 1 over 2 times the square root of x. Right? So again, our f inverse is square root, and so that's getting plugged in, and the derivative of the outside is 2x, and so we're going to be multiplied by 2 down there in the denominator. Okay, let's do the same thing for the cube root. And so for the cube root, our original function is x cubed, and that makes the inverse function the cube root. The derivative of x cubed is 3x squared. Using the power rule, the power of 3 comes down, and then the new power is 1 less. And so again, this should be, say, cube root there is equal to 1 over the derivative of f with f inverse plugged in. And that, again, that should be cube root there. And doing that, we get 1 over 3 times the cube root of x, quantity squared. And so this is what we've got from these two, looking at the square root and the cube root. What about derivative of general root? So if we're taking the nth root of x, what's the derivative of that going to look like? Well, so to get the nth root of x, we're going to start off with x to the n, so that the inverse function is the nth root. By the power rule, the derivative of x to the n comes down, and then it's x to the subtract 1 power, n minus 1. So our derivative is n times x to the n minus 1. And so then when we're doing the nth root, it should be an n there, sorry. Plugging this in, I'll write that n back in, and we're going to have 1 over n times the nth root of x to the n minus 1. Okay, same as idea as before. And so last question is how does this gel with the power rule that we've seen for integers? Well, remember that roots are really talking about fractional powers. So square root of x is really x to the 1/2. And so we saw that the derivative of the square root of x is equal to 1 over 2 times the square root of x. And then we can convert this all into fractional powers. So all the square roots of x will turn into x to the 1/2. Right? And then we can think about x to the 1/2 in the denominator as really being x to the minus 1/2. And x to the minus 1/2 is the same as x to the 1/2 minus 1. Right? And so sort of intermediate step here is that this is equal to 1/2 times x to the minus 1/2. And then minus 1/2 is equal to 1/2 minus 1. And if you notice, this matches the power rule, just with the n being 1/2 instead of an integer. Same thing with the cube root. So 1 over 3 times the cube root of x squared. We can think about that in terms of powers as being x to the 1/3 and then squared. And so really that's 1 over 3 times x to the 2/3. And so x to the 2/3 on the bottom, we can think about this as being 1/3 times x to the minus 2/3. And minus 2/3 is equal to 1/3 minus 1. And so this also matches with the power rule, where we have our old power was 1/3. When we take the derivative, the 1/3 comes down, and our new power is 1/3 minus 1. Same thing with nth roots. So nth roots, it's a little bit hairier, but not too bad. It's 1 over n times the nth root of x to the n minus 1. And so the nth root of x is really x to the 1 over n. So we plug that in. And then when we distribute the power n minus 1 to the inside, really we have 1 over n times x to the n minus 1 over n. And then n minus 1 over n, same as before. We can think about this as being 1 over n times x to the minus n minus 1 over n. And minus n minus 1 over n we can think about as being 1 over n times x to the minus 1 minus 1 over n. And then when we distribute this minus sign, we have minus 1 plus 1 over n. So we can rewrite this as 1 over n x to the 1 over n minus n, which is equal to 1 over n x to the 1 over n minus 1. So same as before, our original power, x to the 1 over n, comes down, becomes the coefficient, and then we have our new power is 1 over n minus 1. So this is the same power rule. So this power rule works for positive powers, negative powers, fractional powers, and in fact, the power rule is going to work for every power of x. So power rule, this is in general, this is how you take the derivative of x to any power. Positive, negative, fractional, irrational, doesn't matter. That is all for this video. I will see you again soon.